Hello everyone, good evening. I'm Amritanshu. I'm co-founder of Extera Robotics. At Extera, we are building legged mobility solutions for different applications. And my talk today would be concerned about the software architecture of legged robots. So how many of you guys have actually seen a legged robot in action? Can I just have a show of hands? Oh, that's a good number. And how many of you have actually actually know what goes behind the scenes in making these robots, do the things that you see them doing? Yeah. So yeah, we have people around. So yeah, so basically these robots which are becoming quite popular in the recent few years, and maybe you have seen a few of these around, maybe in videos, and maybe some of you have seen these robots physically also. We have demonstrated our Swan M2 robot in Roscon for last 2 days. So basically, what my talk would cover is how do we go about designing the software architecture for these robots. Basically, what are the key components that are there in the software for these robots? And where does ROS come into the picture? How do we fully leverage the capabilities of ROS for legged robots? And also, a key point that I would stress on is where we can also do without ROS, right? And make our software perform better by keeping ROS out of the picture, right? So let's just get started with it. So basically, this is roughly how a robot, any given robot moves in the real world. We have sensors to sense the environment. Based on the data that it collects, the robot plans its actions, and those actions are then passed on to the actuators, which then make the robot move around in the real world, and the same loop goes on. So this sense, plan, act loop is basically something which goes on at a fast enough rate in all the robots that you see moving around today. So as far as a legged robot is concerned, and specifically talking about our platform, I will just quickly go over the few key things that we would be referring to in my talk. So basically, the robot is teleoperated with a joystick, right? And it can work in both semi-autonomous and teleoperated mode. The onboard computer is a Raspberry Pi 4B. We have IMU on board and the joint encoders at each of the 12 joints. So those are the 12 actuated joints. And these are what we call as the proprioceptive sensors, which tell the robot about the state that it is in. And we have a depth camera on top of the robot. Right, so this is basically the sensor suite that is there on the robot. Okay, so now typical robot software architecture for a legged robot would look something like this. And this is primarily for robots that are using model-based software architecture. Model-based here means that you have a model of the dynamics and the kinematics of the robot, right? So the locomotion software consists of the motion planner, the estimator, and the controller. The perception and the navigation stack communicates back and forth with the locomotion software. And if you are running the simulation, you have the simulation interface, which finally interacts with the robot URDF. And when we are running the actual robot, we have the hardware interface that interfaces our locomotion software with the low-level interface of the motors. And finally, we see the action on the hardware. Right, so first we'll focus on the locomotion software and how the things inside this block, how we can go about implementing that. Right, so looking into more depth into the locomotion software, we have the 3 blocks, as I mentioned, the planner, the estimator, and the controller. And I will just briefly go over what are the inputs and outputs of each of these 3 blocks. Right, so the user commands a certain velocity, which goes inside the motion planner. The motion planner does its maths, right? It computes where the robot has to step next, right? It's a moving robot, so imagine yourself moving ahead. You need to know where you need to step next. It needs to compute how to move its joints, right? So that is the reference state of the robot. It goes into the controller. The controller basically computes what torques it needs to apply at the joints, right? And basically, both the planner and the controller make use of the estimator, which tells what's the current state of the robot, and the state being, let's say, the velocity, the orientation, the position of its limbs, right? And that estimator makes use of the proprioceptive data, which is the IMU, the accelerometer data, the gyroscope data, and the joint encoders. So basically, this is what we will refer in this presentation as the PEC cycle, the planner estimator controller cycle, right? Now, in order to implement this architecture, the first and the, yeah, so basically I just covered this. I would just move on to from this slide. So yeah, so the obvious approach to begin with was to use ROS1. So this is around about a year back. So we are still using ROS1, and we can implement each of these blocks as a separate node in ROS1. Each node would be publishing and subscribing to a certain topics, and basically each of these nodes run simultaneously. And the key thing to note here is that it's an asynchronous architecture in which that the planner, the estimator, and the controller can each have their own separate execution rates, right? So that is one point which we should keep in mind, because that would be relevant in the subsequent slides. So now, when we use ROS, these are few of the common tools that we use, right? We use RQT graph to visualize the connections between the different nodes and the topics. We use ROS bags for logging data. So these are a few very basic tools that ROS provides in order to make the developer's life easier, right? We visualize data using various ROS compatible tools, like I have put in plot juggler here, right? Which is very easy to use and lets me, either stream live data or also play ROS bags. I also use the custom message types that is easy to use in ROS. Right, so I'll just quickly go over these things, because I believe these are pretty standard things that are there and being used in ROS, right? So we use ROS param features, and this is the classic gazebo simulation which we use, right? And the key thing, one thing to note here is that we use custom plugins here in gazebo. So basically, we write custom plugins to get the state of the base, the state of the joints, and the state of the contact of the feet, right? So, and these sensors basically interface with the URDF to get the data from the simulation. So the joint state sensor publishes the robot's actual joint angles and velocities. The contact sensor, they publish what's the contact force on the foot, what's the contact state of each of the leg, which is crucial for the locomotion software. And here we have also implemented our own contact models as well. And finally, the motor controller is basically the block which simulates the final low-level control loop, the PD control loop, as we know, of the actuators. Now, there are a few issues with this implementation that we started to run into when we moved on to the hardware tests with this architecture. So first few issues are with the architecture itself. The first thing is that the synchronization between the different nodes is not guaranteed here. They all are individually running at their own rates, and if there is a mismatch between the data between these three nodes, it can lead to a degradation of performance, especially on hardware where we cannot run each of these nodes at a very high rate, right? And also, if we want to change the middleware in due course of time, then in this architecture it would require a completely rewriting the entire code, because each of the nodes have their own publishers, subscribers. So basically the communication is all spread around the code base, right? And the second set of issues that we run into is, of course, now well known because of ROS1's lack of support for real time and the quality of service features, right? Now to circumvent these issues, basically we redid the architecture of the locomotion software, and herein I would like to highlight what are the key changes that you can also keep in mind if you are developing some software for the legged robots. So basically, the first modification that we did is we made the PEC cycle synchronous. Synchronous in the sense that now these three computations of planner, estimator, and controller, they would happen sequentially rather than going in an asynchronous individual kind of a manner, right? So that's one key change. Now, with this approach, we also made each of these planner, estimator, and controllers easy to switch around, so that made the code more modular, right? And we also implemented a finite state machine, which allows us to easily switch between different behaviors of the robot, let's say moving around, standing, sleeping, or doing a certain task. what we did with the communication interface is that rather than keeping the communication spread around the entire code base, we put the communication code in a separate module, and that becomes a separate and switchable communication interface. And we structured our code to have support for ROS1, ROS2, and DDS, right? So now, my next point relates to basically this is the overview of the Locomotion software. Basically, we have the PEC cycle there, which has the sequential computation of estimator, the planner, and the controller. And the sensor data is read from the communication interface, and the control data is fed back to the communication interface. The communication interface is basically supports all these three schemes, and finally, the sensor data from the robot interface is again fed back and forth from the communication interface. Now, at this point of the development of the software, we had a choice that either we use ROS2 to build the to use as the middleware for the Locomotion software, and the second was to go with the bare DDS, right? And after much discussion and brainstorming, we decided that we should go for bare DDS in the Locomotion software, because the purpose which ROS2 or a middleware would serve in that scenario is served by just bare DDS. So why not avoid the other overheads that ROS2 brings in and just use bare DDS for that part, right? So, so now the way we designed the Locomotion software is that it can just work with the implementation of DDS, right? So with DDS, we have access to all the QoS features. And we still have interoperability with ROS2, because ROS2 itself supports DDS middleware, right? So our take at this point is that we can keep the Locomotion software independent of ROS2. We can just keep it working with DDS, and ROS2 can still access, with ROS2 we can still access the relevant data that we need for other blocks of the software, because DDS can easily work with ROS2. And we tested with this software on Raspberry Pi 4B, and we ran the planner, estimator, and controller cycle at 500 Hertz, and we were able to do that with around 65 to 68% of CPU usage. And we were able to run comfortably our Locomotion software on a Raspberry Pi. We also ran our hardware interface at 500 Hertz, and that also did not take significant CPU usage. Right. And now coming on to the other block of the important block of the software, that's the perception and the navigation stack. And here we are fully leveraging the ecosystem of ROS2, because the tools are well developed and are easy to integrate and implement on the robot. Right. So we are using the NVIDIA's Isaac ROS libraries to do visual SLAM, which takes in the data from the sensors, the depth camera, and the IMU. It passes on the poses to the NVBlocks toolbox, which computes the distant fields, and that goes to the nav2 toolbox, which finally gives us the commanded velocity once we specify certain waypoints. And that commanded velocity is then passed on to the Locomotion software. Right, so quickly going over these blocks as the time is running out. So the VSLAM uses the 2D features of the input images, the landmass and the pose graph, and computes the odometry that is again fed back into NVBlocks. Now, NVBlocks, basically using IMU leads to a significant performance improvement. It also makes it more fail-safe, the visual SLAM computations. This is just one example of robot poses when the robot was going around in a circular path using visual inertial odometry. Now, in the NVBlocks, we put in the depth image, the color image, and the poses, and it does what we call as the scene reconstruction. It gives us the signed distant fields of the environment around the robot, and this we are running on a GPU. Finally, this reconstructed image is delivered to RViz, and it streams the mesh updates to RViz as well. NVBlocks also handles static and dynamic scene reconstruction. So it maintains what is called as a free space layer, in which whenever the dynamic obstacles come in, that layer is being updated. And finally, we also have the real sense splitter because we are using a real sense depth camera, and we are using this splitter to turn the projector feature on and off, which improves the depth quality of the depth frames that are required for NV blocks. So just putting it all together, let me just come to the concluding slides. So as I mentioned, this whole sense plan act loop that goes on in the software of the robot, we are fully leveraging the features of ROS2 extensively in the perception and navigation stack, wherein we are taking data from the sensor to do visual SLAM, and finally the navigation, the nav2 toolbox is giving us the commanded velocities, and which is passed on the locomotion software. In the locomotion block, as I mentioned, we are avoiding the ROS2 related overheads and we are just going with bare bone DDS, and that is working fine for us, right? And finally, the communication interface that we have designed, it allows us to seamlessly operate between the ROS2 of navigation block and the DDS of the locomotion block, right? So yeah, basically that's how we are running our locomotion software and the perception block right now. And going ahead, we would be developing this software even more, and it's likely that we would be releasing it as an open source software soon.